Carl Sagan wrote in Cosmos, "Maybe life didn't originate on Earth. Maybe we're all aliens, descendants of microorganisms that traveled here from distant worlds. Panspermia. We are the aliens we've been looking for." This sentence represents one of Carl Sagan's deepest cosmic insights. It invites us to a fundamentally different perspective. Maybe we don't need to look to distant galaxies to find alien life. Maybe alien life is already here. Maybe it's us. The panspermia hypothesis is radical. It approaches the origin of life from a completely different angle. It suggests life didn't spontaneously emerge on Earth. Instead, it came from space, transported by comets, asteroids, and meteorites, spread through interplanetary, even interstellar travel. This idea isn't new. The ancient Greek philosopher Anaxagoras, in the 5th century BC, proposed that seeds of life existed everywhere in the cosmos. In the 19th century, Lord Kelvin and Hermann von Helmholtz developed similar theories, but modern panspermia received serious scientific consideration in the 1970s with Hoyle and Chandra Wickramasinghe. Carl Sagan was initially skeptical. He believed the origin of life on Earth was possible. The Miller-Urey experiments had shown amino acid synthesis. Organic compounds could form in primitive Earth's atmosphere. But as evidence accumulated, Sagan gradually began to consider the possibility of panspermia. The first compelling evidence was the discovery of organic compounds in space. Radio astronomy began detecting complex molecules in the interstellar medium. Formaldehyde, methanol, even amino acids were found. Space wasn't empty, it was chemically rich. Carl Sagan became excited. In The Cosmic Connection, he wrote, "The stuff of life is everywhere. The cosmos is rich with organic molecules. Life's building blocks are not rare. But finding organic molecules doesn't mean finding life. Panspermia requires living organisms to survive and travel in space. This is an extraordinarily challenging environment. Space vacuum, extreme temperatures, intense radiation, cosmic rays. Can life survive? The answer is surprisingly yes. Extremophile research showed life could survive incredible conditions. Antarctic bacteria surviving at -50 degrees in dormant states for years. Deep ocean organisms tolerating 400 Gorsi temperatures. Bacteria thriving in radioactive environments. Space simulation experiments gave encouraging results. The European Space Agency's Biopan experiments exposed bacteria, fungi, and lichens to space conditions on the ISS exterior for months. Many organisms survived. Some even reproduced. Tardigrades proved particularly resilient. These microscopic water bears survived 10 days in space vacuum. They tolerated dehydration, radiation, and extreme temperatures. After rehydration, they resumed normal activities. Life was more robust than anyone imagined. The Mars connection is particularly intriguing for panspermia. Mars and Earth have similar formation histories. Early Mars was warmer and wetter. Life could have emerged. Asteroid impacts could have exchanged material between both planets. A natural interplanetary transportation system. The Allen Hills 84001 meteorite sparked controversy. In 1996, NASA scientists announced possible biosignatures in a Martian meteorite. Microscopic structures resembling bacteria. Chemical signatures suggesting biological activity. Organic compounds present. Carl Sagan was cautiously interested. At the press conference, he said, "Extraordinary claims require extraordinary evidence." The evidence was suggestive but not definitive. More research was necessary. But the possibility was real. Subsequent analysis gave mixed results. Some features were explained by non-biological processes. Others remained unexplained. The scientific consensus, possible but not proven. Research continues. But the larger principle was established. Mars-Earth material exchange is real. For billions of years, asteroid impacts have ejected rocks from Mars's surface. Some eventually impacted Earth. Interplanetary contamination is possible. Recent astrobiology research has increased panspermia's plausibility. Deep biosphere discoveries showed life existing kilometers underground, with minimal energy requirements and extreme pressure and temperature tolerance. Maybe interplanetary journeys are survivable. Spacecraft contamination concerns are real. Apollo missions possibly transported Earth bacteria to the Moon. Mars missions require elaborate sterilization procedures. Planetary protection protocols exist because contamination is possible. But contamination is bidirectional. If Earth life can go to Mars, Mars life can come to Earth. Maybe it already happened. Maybe it's an ongoing process. Venus's early history is also relevant. Young Venus was possibly habitable before the runaway greenhouse effect. Life could have evolved, then escaped as conditions deteriorated. Venus clouds still contain organic compounds.
Enceladus, Europa, and Titan show complex organic chemistry. Life could emerge, and through impact events, material could be ejected. Interplanetary life transfer throughout the solar system is possible. Interstellar panspermia is even more speculative but possible. Oort cloud comets are occasionally captured from interstellar space. Rogue planets ejected from solar systems travel through deep space. Maybe life hitches rides on these cosmic vehicles. The observable universe contains billions of solar systems. Exoplanet discoveries show planetary systems are common. If life emerges anywhere, the spread potential is enormous. Galaxy-wide biological connectivity is possible. Carl Sagan painted this vision in Cosmos. The cosmos is vast and largely unexplored. Maybe life originated not on Earth but somewhere else. Maybe we're the products of interstellar migration. This perspective fundamentally changes how we think about ourselves. We're not a unique terrestrial phenomenon. We're part of a cosmic biological network. Life is possibly flowing throughout the galaxy. We're nodes in a vast living system. The implications are profound for SETI. If panspermia is true, life is common throughout the cosmos. Intelligence is also more likely. We're not searching for completely alien life. We're searching for cosmic cousins, distant relatives who share a common origin.
Astrobiology mission priorities change. We're not just looking for life on other worlds. We're looking for evidence of biological connectivity, genetic similarities between Earth life and alien life, common biochemical signatures. Recent molecular biology supports the possibility of panspermia. All Earth life shares a common genetic code. DNA, RNA, proteins are universal, maybe because life has a single origin, not an Earth origin, a cosmic origin. The amino acid chirality mystery is intriguing. Life uses exclusively left-handed amino acids. Right-handed versions are chemically identical, but biologically incompatible. Meteorites show a similar chirality bias, maybe a cosmic selection process. The phosphorus scarcity problem lessens with panspermia. Earth phosphorus is limited, but comets are phosphorus-rich. Maybe essential elements were delivered from space, not a limiting factor for origin if there's a cosmic source. Carl Sagan's pale blue dot perspective is enhanced by panspermia. Earth isn't an isolated island of life. It's possibly a colony in a cosmic archipelago, connected to a vast biological network spanning the galaxy. Environmental implications are significant. If Earth life is cosmic heritage, preservation is even more important. We're not just protecting Earth species, we're protecting cosmic legacy, a unique branch of galactic biology. Space exploration takes on new urgency. We're not just exploring for resources or knowledge, we're searching for our cosmic family, tracing our biological ancestry, understanding our place in a living galaxy. Mars sample return missions are critical. If Martian life is found, genetic analysis is essential. Common ancestry with Earth life would support panspermia. Independent origin would suggest life emergence is common. Europa and Enceladus missions are similarly important. Subsurface oceans could be connected to early Earth oceans. Biological exchange through impact events. Comparative biochemistry could reveal relationships, but panspermia also raises uncomfortable questions. If life comes from space, what started it originally? It just pushes the origin question further back. The ultimate origin is still mysterious. Maybe there's no single origin point. Maybe life emerges wherever conditions permit, then spreads throughout the cosmos, a self-propagating phenomenon. The galaxy gradually becoming biologically connected. Carl Sagan believed in life's universality regardless of origin mechanism. Life finds a way was his conviction. Whether Earth originated or space delivered, life represents the cosmos's tendency toward complexity. Modern research increasingly supports life's resilience. Extremophile discoveries are expanding habitability definitions. Subsurface biospheres are common. Space survival experiments are succeeding. Organic compounds are everywhere. DNA analysis is revealing unexpected connections. Horizontal gene transfer between species is common. Bacteria share genetic material across domains. Maybe interplanetary gene transfer is also possible. Quantum biology discoveries suggest life uses quantum effects, entanglement in photosynthesis, quantum coherence in bird navigation. Maybe quantum connections enable cosmic biological unity. If panspermia is true, the abiogenesis problem lessens locally. The origin of life happens somewhere, then spreads. Not every planet needs independent origin. Biological seeding is possible, but it still requires initial origin somewhere. Maybe in the earliest universe generation. Maybe it's a continuing process. Maybe there are multiple origins. Questions remain, but constraints are relaxed.
Carl Sagan's approach: keep an open mind but require evidence. Panspermia is possible but needs testing. Predictions must be testable. Observations must be interpretable. Current evidence is suggestive but not definitive. Space survival is possible. Organic compounds are abundant. Material exchange is confirmed. But living organisms in space are unconfirmed. Future missions will provide better data. Sample returns from Mars, asteroids, comets. Direct analysis of potential biosignatures, genetic comparison with Earth life, molecular archaeology of life's history. The James Webb Space Telescope is detecting atmospheric compositions of exoplanets. Maybe biosignatures will be found, maybe technosignatures, maybe evidence of life spreading between worlds. Breakthrough technologies are enabling better detection. DNA sequencing is improving. Isotope analysis is advancing. Protein analysis is developing. Tools for testing panspermia are improving. But the ultimate answer may require interstellar exploration, Proxima Centauri system analysis, direct sampling of other star systems, search for cosmic biological connections. Breakthrough Starshot is planning interstellar probes, light sails reaching nearest stars in decades, maybe detecting life elsewhere, maybe tracing the cosmic family tree. Advanced instrumentation is enabling unprecedented analysis, next-generation DNA sequencing capable of detecting ancient genetic material, isotope ratio analysis, distinguishing biological from abiotic signatures, protein analysis providing evolutionary insights. Machine learning is revolutionizing pattern recognition. AI algorithms trained to identify biosignatures in complex datasets. Automated analysis of massive amounts of astrobiological data. Real-time detection of biological patterns. International cooperation is expanding research capabilities. Shared databases of genetic information. Coordinated sample return missions. Global astrobiology research networks. Combined expertise advancing understanding.
Whether panspermia is true or not, the concept transforms our perspective. We're connected to the cosmos through chemistry, physics, and biology. Star stuff becoming aware of itself. Cosmic evolution creating consciousness. The implications for human identity are profound. If we're products of cosmic biology, our origins stretch back through interstellar space. We're not just terrestrial beings, but cosmic citizens, children of the galaxy carrying ancient biological heritage. This perspective changes how we view our responsibilities. If life is a precious cosmic phenomenon, preservation becomes even more critical. We're not just protecting local ecosystems, but safeguarding galactic biological diversity, stewarding cosmic legacy. Space exploration takes on deeper meaning, not just technological achievement, but biological pilgrimage, searching for our origins among the stars, reuniting with cosmic family members, understanding our place in living universe. Environmental protection gains cosmic significance. If Earth represents a unique branch of galactic biology, conservation efforts protect irreplaceable biological heritage. Preventing extinction means preserving cosmic information accumulated over billions of years. Carl Sagan's message endures. We are a way for the cosmos to know itself. Whether Earth-born or space-delivered, we're cosmic phenomena, the universe experiencing itself subjectively through our consciousness, looking at the night sky differently with panspermia perspective. Those stars are possibly connected to our origin. Those planetary systems are possibly our ancestral homes. Every point of light potentially harboring our cosmic relatives. Meteor showers become more meaningful. Maybe not just cosmic debris, but biological delivery systems. Comets appearing in our skies, possibly carrying seeds of life. Asteroid impacts potentially reseeding events rather than just destruction. The search for extraterrestrial life gains personal dimension. Not just scientific curiosity, but family reunion. Discovering alien life might mean finding our cosmic cousins. Biological relatives separated by interstellar distances but connected through common ancestry. Maybe someday we'll confirm panspermia, trace life's journey through space, understand our cosmic heritage, reconnect with the galactic biological network, discover we're part of vast living system spanning galaxy, or maybe we'll discover Earth's origin is unique, life emerging independently here through special circumstances creating consciousness, an equally profound realization about our cosmic significance and responsibility. Either way, the search continues. Questions drive exploration. Curiosity motivates discovery. Carl Sagan's legacy inspires investigation. Wonder about our origins propels scientific advancement. We are made of star stuff. Whether life started